Okay, so yeah, let's get started. Also welcome everybody from my side. So I'm Jan Hoffmann. I'm an assistant professor at Carnegie Mellon. So my research interests are programming languages, obviously. So specifically, I'm interested in quantitative properties of programs, like things like resource usage or probabilistic programming. So these are things I do research-wise. It's nothing I'm going to talk about today. I also do teaching, so I teach at CMU the Principles of Programming Language course and also compiler design. All the lectures, in this week, I think are based, at least the topics of the lectures are covered in this book, Practical Foundation of Programming Languages. So for instance, there's also this E-language that Paul introduced, and so there's a PDF online, so if you Google that, you'll find it. So that's a good source, like if you want to read a bit more about the topics, that's a place to look.
Jan,
yeah?
Louder.
Okay, louder, okay. Speaking of louder, so writing that big is a bit larger than I'm used to. So during the lecture, I'll probably, it will get smaller and smaller, and then you have to, shout at me larger, and then I'll start writing larger again. Last thing before we start is lunch. So if you, wanna have lunch with me, then you can just come after lecture and invite me to join you, and then you can ask me anything about programming languages, doing a PhD, Carnegie Mellon, whatever you want to know. Okay, so just find me. Okay, so the topic of today is what is a programming language? So that's a question for you. What is a programming language? Can it exist without a computer? So what is it then?
Rules.
Rules, yeah, that's pretty good. So the point we want to make today is, or like maybe in the whole week, okay. Thicker pens.
Can I take a crack at the question?
Yeah.
A programming language is a system of expression for imperative knowledge.
System of expression for imperative knowledge. Well, I wouldn't be that ambitious at first, so I'm not sure if that's an improvement. Where's the writing here? Yeah, I think these are worse. A bit more general. Programs are mathematical objects. So we, define them using mathematical definitions, and you've already seen one part of it. Okay, another version, which is the definition of the syntax, and what we see now is how can we define the meaning of programs. So the meaning of programs is completely independent from any implementation, from a compiler, from an interpreter. It's just like a mathematical definition. And then when you implement a language, you want to have an implementation that is faithful to the definition. So this is the point of view that we're taking here. Okay, so how do we define a programming language? So you've already seen the syntax, and in this lecture we see the static Okay, so which answers the question, what are valid programs? And then we see the dynamic semantics. That asks the question how to run programs. Yeah, this will be probably after lunch, and that's what is defining our language. So you could say like, oh well, the static semantics, isn't that already defined by the syntax what a program is? Well, not quite. We had the question in the first lecture where we said like, what happens if you add two booleans? So that doesn't make sense. So should that be a program or not? And this question is answered by the static semantics. So let me maybe, just for reference, write down our syntax again of our language E. So an expression was a variable, right, or a number, or a bool, either true or false. Then we had conditionals. Then we had the let. So the x is a bound variable. So now we always identify programs up to alpha equivalence, and when I do substitution or something like that, you don't even talk about it. So they're, for us, no issues with that. Okay, this is all like resolved now. And what did I forget? Oh yeah, right, the two operations. So we have plus, and then we also have the less or equal. Okay. So now the static semantics will say like, yeah, so our starting point is like the set of expressions that is defined by this grammar, and we now want to like identify a subset that says what are the good programs, valid programs. So one option would be to say yeah, so we just say all the expressions are valid programs. But so this has like, several downsides. So first, I mean, from a practical point of view, if a program doesn't make sense, like, adding two booleans, why, should we allow it? It's just like, a source of error for the programmer. But even if we take like this mathematical view, it makes sense to exclude these programs from our study, because it makes several things easier. So if we don't have to deal with these like programs that don't make sense, so then the reasoning about programs and definition of like, for instance, the dynamic semantics becomes much easier. Okay, so so this is not ideal. Yeah. Okay, like 5 to true, so that doesn't make sense. So this is something we don't want to deal with later on when we define stuff, so we want to exclude that. So, and the observation here is, I mean, why is that not a program that makes sense? Yeah, because there seem to be two types of expressions, right? So there seem to be expressions that are numbers, and there are expressions that are Booleans. And so this is maybe what we want to do. We want to distinguish them, and we want to say, like, okay, if you have, you know, the addition, you need to have expressions of type num, or that are numbers, that you have to add together here. So the observation expressions have two types. And so this is what we want to distinguish. And we do that by defining a type system. So the type system is part of our static semantics. So let's do an example. So what is the type system supposed to do? So if you look at this expression, so why is this, or like, is that a good expression? Looks good. So why is it a good expression? Right, they're all the same type, they're all integers. So if we start at the outside and we say, like, okay, we have an addition here at the outside, right? So then we have to check if we have numbers in the left position and in the right position here. So so why? Of course, because 1 plus 2 is a valid expression, and it's a number. And also, it's a valid expression. So now you can again ask, why is that? Well, so 8, that's pretty clear, that's a number. And then, we have to, look at this expression here, and okay, so now we can do the same reasoning again. It's a, addition. The result should be a number. The arguments are also numbers. Yeah. So, and if you want to define this mathematically, something like that, what comes to mind? When you see, like, okay, so now we have like this sub expression, and we do the same thing again. Recursion or induction, right? So you want to define the type like that. So okay, so So in general, can already introduce some, maybe I'll write it here. Notation. So what was our example? So we would write that this expression has, type num, so that means like it's a valid expression and the type of it is it's a number. And just like the notation for us to write it is like this, okay, it has type num, and in general, we write things like this, an expression has type tau, yeah. And we call something like that a judgment. Okay, and this is what we want to define inductively. Okay, so and this is something we do in PL all the time. We have judgments, and we define what they mean by induction. Okay, and so this is something before we continue to do that, and we define our type system inductively. I want to have a short intermission and talk about inductive definitions and how we do that. So we keep that in mind. Inductive definition. And so let's do an example. Binary trees. So we want to inductively define the set of trees. So what do we do? So we say okay, the empty tree is a tree. And we want to store, let's say, natural numbers in our tree. If I have a number and I have two trees, T1 and T2, then node n, let's do n first, T1, 2 is also a tree. Okay, that's an inductive definition, and I think it's pretty clear to understand, and it defines, if you want, a judgment. That looks like this, yeah. A judgment can have, any form. It can say n is a natural number, t is a tree. It could be, of the form, like this. It's simply like a predicate. Okay, so this judgment is defined inductively, and so what does it mean to define something inductively? So the usual way to say it is you define a set, and it's the smallest set that is closed, under the application of these two rules, 1 and 2. Okay. Induction. So, what we usually do in PL, so I mean it's fine to write it like this, but what we usually do, because things, the definitions get more complicated, we use rules. So we express the same thing, but we use these inference rules, okay? So they, in general, have a form. Yeah, so they are like, first of all, I mean, for so they are for inductively defining judgments, and they have the form that looks like this. They have premises, so the things on the top, and judgments, and they have a conclusion. This is one judgment at the bottom. So these are premises. This is the conclusion, and this is nothing to be afraid of. It's just like, the plain old inductive definitions that you know. So let's go back to our tree. How would we write that, down with these rules? So that would look like this. So the first rule would say amp is a tree. And the second rule, let's say, okay, if n is a number, so you can also use like other judgments here. T1 is a tree, then node n T1, T2 is a tree. So this is just a alternative way to, write this inductive definition. Yeah, question?
So for judgment that holds for all premises, is that like an axiom?
Uh,
What would we call it?
So you're asking if like the M tree, if that's an axiom? Yeah, right. You can call that an axiom. Yeah.
What's the difference between like turnstile and horizontal bar? Turnstile, like the one that you have over there.
Right.
Are they the same thing?
No, the turnstile kind of like means you can derive this judgment. So it's not the same thing. The horizontal bar means like, okay, this is one rule, but now, okay, we can do that. Right now, let's see. Okay, maybe have to. Oh, maybe I can squeeze it in here. So derivations. So this is what we usually write with a turnstile. So now you wanna prove to me that, for instance, let's say node so of 0 amp. So I say, well, I'm not convinced. So, and then, what can you do to convince me that this is a tree? So you have to use the rules to derive this judgment. And this is what we usually just write like with this turnstile. So, yeah, so if you want to, show me that this is a tree, you have to apply these rules. So which rule do you have to apply here for this one? Yeah, the one on the right here. So let's call that one, and that one 1. So what you want is to apply 2. So what you have to show is that the successor of 0 is a number, that amp is a tree, yeah, I'm just copying what's written there at the rule, because like, yeah, this amp is a T1, this amp is a T2. Okay, so what's next? Have to use more rules, so now we're not done yet because we have to show that amp is a tree, but that's pretty simple because it's an axiom, as we learned. So here we just apply rule number 1, done. Here we do the same, and I didn't give you the rules for the natural numbers, but you can already imagine how they are. So here we would use the successor rule, and here we would use like the 0 rule, and then we know that this is a natural number. So this illustrates hopefully the concepts of judgments, inference rules, derivations. Yeah, and this is just another way to write down inductive definitions that you hopefully already know, but if not, also not a big problem. So I said earlier that like usually with these inductive definitions we say like it's the smallest set that is closed under like these two rules. So how does it relate to this other view here with the derivation? So I seem to suggest that everything is or like everything that or the things that are like defined by this judgment, the things that are trees, are exactly the things that have a derivation. And these definitions are equivalent. So that's up to you, how you want to think about it. You can think of like this, yeah, the smallest set that is closed under the application of the rules, or you can think of like, all things are trees that have such a derivation. Yeah, it's equivalent. Same thing. Okay, so this is, if there are no more questions, so then this is the end of our intermission. Yeah, so then we go back to our problem where we wanted to define this type judgment here inductively. And of course now we're going to use these inference rules to define it. So, yeah, maybe. So, well, let's say type rules. So let's maybe start with the axioms. So we would say that numbers have type number. Okay, that's pretty clear. The have type bool. So next one are the variables. So what's the type of variable? So that's a bit weird. So the type of a variable can really be, multiple things. That depends on the context, right? So if you have this one, well, then the variable should be a number, right? And if you have this one, well, then it should be a Boolean. So this judgment we have for our types, it's not really good. There, we need to somehow keep track of the variables that we defined in the program, and then we want to, if we determine the type of an expression, we need some kind of context in which it appears. Otherwise, we can't determine the type. So what we add here to our type rules is a context gamma that keeps track of the types of the variables. So if we see a variable, then we would look it up in gamma. So let me, maybe write it like this. That just means, we have recorded that, x has type tau in this context, and then we know that this expression has type tau. So in general, the judgment that I wrote there, maybe I squeeze it in here. So the type judgment looks like this. And so this is a context that maps variable types. Yeah, of course, it's a mapping, so every variable has at most one type. You can't have a variable in there that has two types. That wouldn't make any sense. Yeah, so every variable has a unique type, and so of course E is an expression, and tau is a type. So we say, expression E has type tau in context gamma. So, and you can, so this is sometimes what we call a hypothetical judgment, because gamma contains the hypothesis, the assumptions, that the variables have these types, and under these assumptions, the expression E has this type tau, but for our purposes, you can also think of it just as a judgment that has three arguments, this gamma, the expression, and the type. So that's also fine. Okay, so the other rules are more or less interesting. So an interesting one is, of course, the let. Let's do that one. So you have some context. So maybe you can help me with writing this rule. So, what should be the result of what type should the result have? How is that determined? E2, right. So it should basically be the type of E2. So, right. So E2 should have type tau. Yeah?
Why do we make gamma explicit? Why can't we just assume type gamma?
Right. So, why do we write it? Because it changes. You'll see that now. So what should be the gamma under which we type the E2? Right? So definitely, we can use all the things that we have in the context currently. That's clear. But what else can we use? Inside the E2, what other variables can we use? X. Right. So, and what should be the type of X? The type of E1. So let's call it maybe tau 1. So that should be the type of E1. and the context is just a good old gamma without anything else. And that's why we need to mention the context, because it changes as you go along. As you go like inside your expression and you see all these lets on the way, you make the context bigger and bigger, you collect all these types of these variables, right, because they can appear in the inside. So this is how this rule works. So one thing that's interesting though here is, so what, or like maybe somebody of you notices, so I mean, what's a bit weird about this rule? So what happens if the x already appears in gamma? I mean, we just said the types have to be unique, so maybe there's already one in there. I mean, I didn't really tell you what this kind of like notation means. It just means like that you extend the context with a new mapping, x to tau 1. So, but if it's already in there, you have a problem. So then this is kind of undefined. But we don't care about that anymore because alpha equivalence. So we just assume that this doesn't happen. We say like, all bindings are unique. If there's like a name conflict, well, we just rename. Okay, so. Yeah, and this is like why this, alpha equivalence is so important, because, it shows up everywhere. So what other rules do we have? Let's maybe do the plus. So that's an easy one. So again, we can have like, some. So now we know that the result of the plus should be a number. And then, inductively, we have to do what? Right. The type of E1 and the type of E2 should be num. Under what context? Gamma, just the same. I mean, what else can we do? There's really no option here. Okay. What else do we have? Maybe another one. So the one for the less or equal, I mean, it's clear, it's very similar. Then we have one for the conditional. So, and that one is a little, let's say. So how does the conditional work? Right, that's a good point. Yeah, the type could be like either the type of E1 or the type of E2. Yeah, that's exactly the point I wanted to make. But for somehow we have to make a choice here. We have to pick one. We don't have the options to say like, well, it's either this or this. So what we do, and what's usually the approach, is to require that the E1 and E2 have the same type, namely tau. But this kind of, I mean, if you think about it, I mean, that seems to be not really justified. Yeah, it could be. I mean, it could be maybe that you wanted to write a program. Let me write it here. That. Yeah, maybe you want to write something like that, so it's always going to be a number, but then it's and that's what you get from a type system. You have a little bit of a trade-off, right? So you get like the guarantees that we're going to talk about later about your programs, but there are some programs that might be good, but that you cannot write. Yeah. So this program is excluded by this rule, because the sub-expressions here. So this is the E1, right, and this is the E2. Yeah, they have different types. It's the same tau. Can't type that. So here, to finish this off, the last one, E has to be type bool, right? Okay, great. So this is our first type system, and now we can look at type derivations. Here, there's a question.
Is the other gammas above and below the lines the same?
Yeah, these are always the same. So if it has like the same name, then it's the same. It's the same like with like this type, tau. They're all the same, right? And if they would be different, like in the let, then I write tau 1. Sure that they don't have to be different, but they are potentially different.
But you're throwing away the result if it's a type of tau, because it's not recorded into gamma, right?
Right. So do I? No, we don't throw away any information. Place where you kind of like have to keep track of a type really is in the let case, where you use something later. I mean, that's the only quite true where you have to keep track of the type. Yeah, I mean, what else do you want to know? I mean, information. Okay, so let's look at a type derivation. So you've seen already one derivation for these trees. Question? Yeah, where? Yeah.
So, like in some programming languages, we want to do operations on different types like number and float.
Yeah.
So in that case, we might use a set of types which could be similar when we are operating on them, or like how do we define it in a formal way?
Right, so in the formal way, I would just say, the easiest is to not do that. Just like assume, in the syntax, you have like a different operation for float and for int, and so on. That's the, cleanest way to do that. And you can see, like, this is how it's done in OCaml, for instance. Right, that's not how it's done in C, but C does not have a very strong type system, right? So it's not a type-safe language.
How can we make it, safe by formally giving this? Like what
Right.
stops us to give a valid definition?
No, nothing stops us, but like it's just like it gets more complicated. So for instance, one approach to do that is type classes. That's for instance something they have in Haskell. You can do it with this, but it's more like a bit of an advanced feature that we will not, talk about probably in the whole summer school. But so there are ways of dealing with that if you wanted, for instance, type classes. Yeah. I mean, you could also say that you overload it, right? So you could also say that, you have like two different type rules for the plus. And then you say like, okay, if the, both arguments are floats, then the result is a float. That's also something you could do, but I would not recommend that. It's a bit messy. It makes type checking and type inference harder, and it's better to avoid it. Okay. Okay, let's do a type derivation. Let's see. Yeah.
On the right side, when we say expression has a type of tau, does that mean like all the variables in this expression are type of tau?
No. If an expression has type tau, it doesn't mean all the variables have to have type tau. So for instance, to give you an example, something like this. Yeah, so the type of the expression is bool, but the type of the variable x is num.
Or how can I define the type of expression as what kind of type?
So come again.
If I want to say expression is a type of tau, which depends what, how do I find out like the type of expression?
So
How do I know like this type, this expression is type of tau, like you said?
Oh, how do you find out what the type of an expression is? Well, so you have to. Okay, so that's a good question. So you have to cover. If you don't want to do that manually, you want to do it automatically, then you need type inference. Automatically find out what the type is.
Yeah,
But
for example, the net you're given there, you say it's a bool type, but for me, like I could say, I don't know, like why not it's another type, because x is equal 5.
right, so the type of the expression is always like the type of the result. Okay, and the type of the result is either true or false here, so the type of the expression is Boolean. And that doesn't do anything with variables that appear in there. Okay, yeah, so the type is always the result type. Has nothing to do with like, you know, what's going on in the computation. So, yeah, maybe I can use, what we're doing on time. Yeah, so maybe I can use that one. A different one here. Yeah, maybe let's use this example to do a type derivation. So what I claim is that this expression with the empty context has type bool. Okay, and this dot just means empty context. And yeah, well, how can I show that? We have an inductive definition. So, you know, and this is a judgment that's defined inductively. So to prove that it has like this type, I can give you a derivation of this judgment. And that's what I'm going to do. And you hopefully going to help me. So okay, over there on the left are the type rules, and what are my options? So which rule can I apply here? Right, the let rule. Is there any other rule that I can apply? No.
Well, there's less than or equal to.
Right, there's less than equal to.
That's too deep right now.
Right, exactly. But that doesn't apply here because it would say like that the expression is a let or is a less or equal, which isn't the case. It's a let. So, and if you look at the rules, I didn't give you all of them, but almost. I just didn't give you the one for the less or equal. We say the rules are syntax directed. So you have, you know, you only have to look at what the outermost expression is, and you know exactly what rule to apply. Here in this case, the let rule. So there's no ambiguity Yeah, doesn't have to be like that, so that's not, you know, a necessary property. You could have like also some, you know, for instance, structural rules, we call them, that you can apply to every expression. But here, this is not the case. We know exactly, okay, here we have to apply the let rule. Okay, so let me maybe just, you know, didn't give the rules names. So, okay, and then we have to look at the premises of the let rule. So here at the bottom, this is the conclusion of the rule, right? And then we have two premises. So what do the premises say? So in this case, which one is E1 and which one is E2? X equals to 5 is E1. Yeah, so I'm saying it already, it's just 5, right? So, okay, so then I have to use the empty context, this is gamma, and 5 has to have some type tau 1. In this case, it's probably number, right? So, and what is the x2? Right. So, yeah, you can see I'm a little bit sloppy here because I use the different syntax than from what I wrote here. So we say, you know, this is the abstract syntax, and I'm using the concrete syntax. So that's not very good, but I can fix that, you know, here I would just say, you know, this is an abbreviation, right? So that's what I'm using here in this like derivation, and in the rules I actually use the abstract syntax. So sorry about that. So okay, so then this is the E2, so what type should it have? Bool, yeah, that fits with the rule. It's the same tau down here and up there. So that looks already pretty good because I'm relatively sure that this expression here has type bool. So now what should the context be? So now, yeah, right, now we need the x in the context. And what is the type? Num, exactly. Great. So now we're not done yet. Now we have to continue. So here on the left side, kind of like the E1 side, we don't have to do much because we can apply the rule up there for the num. It's an axiom. So here we are basically done. So I just say, you know, num, done. And for the, yeah, less or equal, I didn't give you the rule. So maybe that's the only one I didn't write. So of course that had to come up because of the question you asked. So I have to write it here now. So this is here as a side remark. Yeah, it's exactly like the rule for the plus, except that the result is a boolean and not a number. So, okay, so then we have to use the rule again. We have to identify what is the E1, it's x, and the E2, 6. So let's do it in the right order. So x is a number. Six is a Boolean, and the context is still the same. Yeah. Oh, 6 is a number. Of course, this was just a test. Yeah, good. So you're watching out. Good, yeah, this is a type derivation. So that's what you've seen. So to recap, so yeah, we want to define a type system. We want to do it like inductively. So we first, come up with a judgment. Then we have these rules that, inductively define the meaning of this judgment. And then, we can use it to derive types for our programs, in this case, our expressions. So this is how we do it. What was interesting is that we needed this context to keep track of our hypothesis of the types of the variables, as you can see here in this derivation. So what we can do now is we can prove some properties of our type system. So the first thing I would like to prove, maybe use this one here. Maybe I write it down here. We don't need any more. For every expression E, and every context gamma, at most one type tau, such that E has type tau under gamma. So types are unique. So I cannot, if I fix a context gamma, I cannot derive two different types for the same expression E. So this is not possible, and this is clearly something you want, because otherwise, there would be something wrong with a type system. So, yeah, how would you prove that? I mean, maybe you can keep thinking of it, but an easier question would be, why do we have to mention this context gamma at all in this judgment? So isn't the type of every expression unique anyway? At letter changes? Or let me ask you differently. So can you give an example of an expression that has two different types in different contexts?
X.
Yeah, right, X. Yeah, very good. So, right, so you really need this context there, right? Because if you would be allowed to have two different contexts, right, you could have this one. And you could also have this one. Yeah, and then you have a counter example. So you really have to fix the context, but then the types are unique. Okay. So yeah, how would you prove that? So keep again the lemma in mind, and do another excursion. Okay, rule induction. So you all know induction over natural numbers, I assume, right? So first, or like, well, let's say to, show P of n we have to prove two things. First, the property we want to show holds for 0, and then we have to show this like inductive property, so that like if the property holds for n, then holds for the successor of n. So, but if you look at that, so that's, I guess, something you're familiar with. But if you look at the inductive definition of what a natural number is, right? So what is it? So it's defined by inference rules. So you say 0 is a natural number, and if n is a natural number, then S of n is a natural number. So this induction principle is, the principle of like rule induction, if you want. So the rule induction, it works like, well, you have to, go basically through all the rules that you have, and you have to show your, property P for the conclusion of the rule, and you can assume that it holds for the premises of the rule. So if you've done that, then you have proven, your property for all the, objects that are defined by the judgment. And there are again two ways of, viewing this. So one way to view it is kind of like if you do such a proof, you actually do a proof kind of like by induction on the derivation. Yeah. So you look at like, okay, you want to prove something for every natural number. So you look at all the ways you could derive the natural number. And in every case, kind of like your proof should say, why does it have the property, right? And when you do the induction here, well, you say like, well, a derivation of a natural number either ends with this rule, okay, so I know the property holds, or it ends with this rule, so I can assume the property holds for like the thing that was like derived up here, so I know already it holds for this one, and I show that then it also holds for this one. So that's like one way to view it. But you can also view it again like with this like set view of things. So you can also say like, well, what you show really is that like, the set of the, objects that have like the property are closed under application of these rules. And because you know that like, the natural numbers, they are like the smallest set, so, that is closed under the applications of these rules. So then, you kind of like, okay, here in our case, you would show that the natural numbers are a subset of this. Yeah. So these are kind of like the two views of it. So like in general, so let's see. So rule induction. So so you have some property P, and you want to show that like it holds, for every, let's say, triples in our case here of gamma, E, and tau, so that they, have been derived. So kind of like, A in this case is like the gamma, E, and tau. So you want to show something about like, these three, and to do that, for every rule so here that looks a bit different from before because I separated out the arguments of J from the J itself. So I want to say like that's actually the same kind of judgment that I have like in the premises. So you could actually also like extend it other premise here, J prime, like we had in the tree. There was also like the natural number showing up. That would be also allowed. Show for every rule that P of A1 and P of AN implies P of A. So that's the same thing as you've seen like with the natural numbers. The only thing that's a bit weird is like if you have an axiom here, then like you have the empty conjunction, which is like true, so you just have to show P of A in that case. But this is the principle of rule induction.
Are you kind of defining successor here? Successor of any property holds for some number A, then it holds for all the numbers.
Right, but now we want to like generalize. So for instance, if you want to prove something about like trees, then the numbers you can't do induction on the numbers anymore. You have to now do induction on the definition of trees. So there's no successor. There's like this amp and the node, right? So and you have to so you can also do induction on the definition of the trees. So how do you do it? Well, first you have to show your property holds for the empty tree. Then you have to show if it holds for T1 and T2, the subtrees, then it holds for node T1 and T2. So that's kind of like the equivalent to the successor. And in that way you can generalize from like doing such an induction for the natural numbers to any inductive definition. May it be natural numbers, trees, or type judgments. So you can do induction on the type judgment, or if you want the derivation of the type judgment. So you'll see it with this lemma how we do it. But that's kind of like this was like the end of this like intermission to just give you a bit background what this like what does it mean to do like induction on like such a judgment. So we call it rule induction. So that's kind of like that if you want to do some reading tomorrow in PFPL with some more examples. Okay, but what's a bit weird here in this lemma? I mean, it's not even so clear what we should prove by induction. So yeah, so there's at most one type. So kind of like this uniqueness thing. So there's a, it's always like difficult to show, yeah.
How would you like enumerate all the expression constructors? Like go back to the BNF list and then actually do, each one of those as basically.
Right, exactly. That's exactly what the rule induction does. So you say like, well, you're already saying like, okay, you want to like do an induction on the derivation of this judgment. So you look at all the derivation trees and you say like, okay, the derivation tree ends, with one of these rules. So this one, and so then exactly, that's how we're going to do the proof. But it's a bit unclear what to show. I mean, like even, let's say, okay, even if we have like the, easiest case, something, like this. So, I mean, our derivation ends, with this rule. I mean, what are we going to do? So we have to reformulate the lemma a little bit so that, it becomes easier to prove this. And this is a trick, that shows up not only in type theory or programming languages. So that's really something, so that you can learn for life. So what we show instead is if E has type tau 1 and E has type tau 2, then tau 1 is equal to tau 2. So and now it's like in a good shape so that we can do induction. And we can do induction now either on this judgment or on that judgment, doesn't matter. So yeah, I'm hesitating because we still are missing one ingredient we need for the proof. And maybe that's the last thing we do. Existence? No. We need a property that's called inversion. And so the proof we're going to do like beginning of next lecture. And now the last thing I want to tell you here is about inversion. So that's all good. So we're going to continue to do that after lunch. So the problem we're gonna have in this proof is, so we're gonna say like, okay, do induction on this type judgment, and let's say the rule that was applied was like the variable rule, right? So okay, then and then, well, maybe let's do it. So to show you, so case like var rule. So we go through all the rules, right? And then we know that E has a shape X, right? We know that gamma is gamma prime X tau tau 1, right, these two things we know. So then what we want to say is like, well, if E is a variable, then in this other judgment here, we also have to use the variable rule. And then kind of like we have the same situation there, namely also that like, you know, the context must have this shape and so on. And to be able to do that, basically, we need to know that there's only one rule that applies to variables, basically. And this principle is called inversion. So that means like if, you know, you have derived something for a variable, it was like, you know, with a variable rule, and you can assume that you have the premises in there. So, for instance, okay, example. Inversion that's a bit clearer for so if you know that you have some type derivation for, you know, the plus, then you know that the resulting type has to be num, and you also know that you have the premises of the rule, namely E1 has to have type num and E2 has to be type num. So why? Because there's only one rule you can use to derive that, and you must have used this rule. And how can you show that? You can also prove the inversion lemma by rule induction, which is very weird because it's not really some like, you know, you don't really need some like inductive premise or anything, but yeah, I'm telling you, you can do that. It's nothing that I want to do. And like, you know, similarly, you know, for the variable case, like it's the same thing, right? So then, you know, what you know, if it's like a variable, then you know like, well, the variable must have appeared in your context with the same type, tau, that is like the type you derived for this variable. So that's the inversion lemma for the variables, yeah? Right, because, so I mean, I didn't prove the lemma, right? But the intuition is, first of all, there's only one rule you could have used to derive this. And this must be the rule for plus here, right? And so the only type you could have derived was like num. And the only way you could have done that is like if the E1 and E2 also had type num under this context. So that's kind of like the intuitive argument for it. And if you want to make that formal, you have to do like a rule induction, and you basically go through all the rules, but that's basically what the proof does too. So it's kind of like a boring proof. You say like, well, you know, case variable rule, oh well, does not apply, then like, you know, the plus has to be a variable, so that's a contradiction, no. Go to the next rule, same thing until you come to plus, and well, oh yeah, in that case actually the tau is num, and so it holds. And so that's how you prove this.
Basically, we are assuming for the statement, and we are saying that this assumption could be true only if below statement is true.
Right. Okay, good. So then we'll, so beginning of next lecture, we'll pick up again on this lemma, and then we will prove it by rule induction using everything we learned, and we're going to use the inversion, and then we're going to look at the dynamics. Okay, that's it.